When I give talks, I like to honor the place that I've been. So this is just around the corner. It's the Kennedy Memorial. And Kennedy was here on the day he died. And I tried to Google it last night, that he gave a talk about, no, no, wouldn't we wish? No, he gave the talk about his space plan, and he called it an audacious goal. And most people think of it as landing on the moon, but the most important part of it is actually about, and he was a little sexist back then, but bringing the man back safely to Earth. And I think that's related to what we do. Ex situ conservation is an audacious goal. Did you like that link? So we're going to land these seeds in storage, and then we're going to bring them safely back to the Earth. That's our goal. So I'm going to talk to you a little bit about that. It's not just about making collections. It's about using them and bringing them back. It's a lot of rain out there. We don't see that much in Fort Collins. Okay, so what that means is that the survival of the seeds is imperative, and that's what I want to talk to you about, and how long. And that's what I spend most of my time on. So, preservation. This is, I'm trying to be literary here. Don't get out much. Okay, this is really an interesting book if you put it in the context of preservation, because ice 9 is lethal. I mean, if it forms ice at 45 degrees centigrade, usually ice forms at 0 degrees centigrade. And because of this, the whole world solidifies. It's interesting to know that Kurt Vonnegut worked with Langmuir, who was the father of polymer science in the 1920s, and he got his ideas about this. It's a material sciences kind of question. So I'd like for us to move in that way and to think not like botanists, but like material sciences. And what does it mean to be a solid? A solid is actually about putting molecules together. Doesn't matter how you do it. It used to be we would think that they were put together in a regular fashion, and there is some regularity here, but it doesn't really mean that. It just means crowding molecules together so that they can't move. And you know this intuitively by a traffic jam where your neighbor's car is blocking your car. And what that does, it slows things down. You know that. So, in PChem world, we can describe this pretty simply by what we would call a phase diagram. And so here's a pretty basic phase diagram for a material that is a biological thing. I don't know if this is going to work for me. No, I wanted the light there. So we know, from when we were in grade school, what are the phases of of matter, solid, liquid, gas, and the really in material science we're really going to fluids and solids, and within those two there are more complicated phases. So work with me with the solids part, because that's what we're going to talk about. And we know intuitively when we're talking about water that there's ice, and that's crystalline. But there's also these other types of solids that form just by crowding molecules. You just remove the water and all the molecules just kind of stop themselves. And colloquially, and I might slip into that, we would call that a glass. Just like glass in the window, except it's a biological glass. And glass is, you can think of it as a plastic. There's lots of words. The material science is very vocabulary laden, just like any other discipline. Okay, so here's the phase diagram, and you will hear this over and over and over again when we talk about seed storage. Dry it, cool it. So that's what we're talking about here. This is 100% water, and this is completely dry. And here is high temperatures, and this we're getting to be the temperatures of liquid nitrogen. And most of the instrumentation I use, minus 150 is about as low as I can go, so that's usually where I stop my graphs. It's also nice and round. Okay, so you know about water freezing, pure water, 0 degrees, and you form ice. But if you dry that water, that solution, or concentrate the solution, that temperature goes down a little bit. A lot of people don't think about how water behaves in forming solids. We can call that vitrification, hence the glass. Or if you go the other way and you have a solid and you add water to it, it would be plasticization. And that word is just, plastics, they move, you can mold them. So it actually is intuitive if you care to think about it that way. Okay, so there is the model. Seeds are the original material scientists. I mean, they're engineered to do this naturally. And they do it during their embryogenic program, where they're just accumulating dry matter. Think molecules crowding together, right? And so by the time they have vascular separation, that's where mass maturity is, their cells are just chock full of dry matter, and that is why they go into quiescence, i.e. those delays we were talking about. And if you look at it in the electron microscope, you can watch that whole program, and I'm just going to show you a couple of pictures of cells. They start off with these huge vacuoles and nothing in them, and this is just after pollination. And then the beginning of dry matter accumulation. These guys are dry matter accumulating machines. That's what they do best. Maybe that's the secret. I think it's the secret. At vascular separation, they are full of stuff. Oh, my good slides. And then by the time, just before drying, if you look at this, you can't even tell where this is a phaseolus, so it's starch and protein. You can't even tell that there's a nucleus in there. It is just full of stuff. Chance or pattern? So what does that look like in a cartoon? Here it is, full of dry matter. And if you dry this stuff down, there's virtually no mechanical stress or anything. The seeds just dry down. They keep their shape, but they remove water. That's pretty cool. And they do it naturally. So, point number 1. What we have to do for preservation is turn the cytoplasm from a fluid to a solid without killing it. And most seeds that we work with do that naturally. How good for us. Not all seeds do this. I've been with CPC since the early 90s, and recalcitrant seeds has been like this huge thing for them of how do I know my seeds are not recalcitrant. And we know that, and we actually understand recalcitrance much better now. And what does that look like on the cartoon? They don't have a lot of dry matter in their cells. So when you dry them out and you try to form that solid, they shrink, and there's just all kinds of stress, and they don't make it. This is all going to be online, Sean. I'm really glad that you like it. and you promised you wouldn't fall asleep, so I like that too. We got to make it real here. All right. So here we are in part 2 of the literary. This is the Tale of Two Cities, and what I'm going to do is put the seeds on this phase diagram. Here we are, the orthodox seeds. They dry down. Yay. And here's the recalcitrant seeds. There's no hope of preserving them this way because they don't form the solid the way they have to in order to slow down the molecules, in order to cause things just to be slow. Okay. So we're going to tell more about these. This is what we do when we store seeds. We dry them down, and then we cool them down. That should be really familiar and intuitive to you. If we did the same thing to our recalcitrant seeds, and this is why people are so afraid of them, if we just cooled them down, because if we dried them, we kill them, then the ice forms and they die. That's a bad day. So we don't want to do that. So what we can do with them, and this is the last I'm going to talk about it, is we can dry them a little bit, and then that difference between where you have ice and when you can get into the amorphous state, it's really narrow temperature range, so we can cool really, really fast, and we can do it, and we can cryopreserve. We can cryopreserve with high survival just about any recalcitrant seed if we can play with the geometry, and so that means excising the embryonic axis because they're usually big seeds, and if we can optimize this moisture. So we're pretty confident. When we start getting into tropical material, it gets a lot more difficult because they have a lot of metabolism. That recovery becomes difficult. But for North American temperate species, we're getting about 80% survival to 100% survival. So that's the story in recalcitrant seeds. And now we're just going to talk about these orthodox seeds because I think that that's what Joyce charged me to do. And I always do what Joyce tells me to do. Okay, so life in the traffic jam. Very annoying. And things do slow down, and it's frustrating. And I think you got to keep that idea of the frustration in your mind because molecules get frustrated too. What we can do is talk about the mobility of the molecules. And this is, by the way, scaled, and I've measured it, and I measured it with a certain... it's a lot of math and PChem. But this is in the dry state. That's a lot of motion happening in the dry state, even if it seems pretty stiff. But you can see I'm lowering the temperature, and the molecules are slowing down. And here we are. This is as low as I can go with the models and the calculations with the instrumentation that I used. But this is minus 135, and you can see that there's still some molecular motion happening. So this is an important point to take home, is that even though you think you're colder than anything and nothing can happen, actually we can measure a lot of motion. So usually I take a drink of water here. Okay, so what's actually happening? Another cartoon. We've got these molecules, and they've all messed up, and they're trapping each other. But what they're going to be doing, and we know it's happening, is they're going to be changing with time. And usually in the glass, that those pores that form, because it was imperfect packing, those are just going to compress with time. And so you can see that it's just slowly moving. There's a couple of things that are going to happen with that. One, molecules are going to get closer together, and that glass, those properties, are going to change with time. I think I'm supposed to click this now. Let me just see if it works. Yeah. So the structure gets denser with time, and we can measure this. We can actually measure how things are changing, but it's really, really slow. Okay, I talked a lot about frustration of these molecules. Oh, I wanted to go back and make another point. You can still see, even in my little cartoon, that there are these pores. And these pores are really, really important. Just keep that in mind, that it's going to continue to compress because where there's a vacuum and when there's space, if it's not perfect packing, it's going to change. It will change, in fact. Okay, so here's the model of these molecules that are all pressed together. And this motion of them moving, we call that diffusive motion, okay? It's molecule go here to over there. Translational motion, there's a lot of words for it, but diffusion is good. If you don't have diffusion motion, those molecules are frustrated. I mean, people are moving in their cars. You just can't see it because they're stuck in their cars. But I like to think of it as shaking, or they're rotating, or they're playing with the radio, or whatever they're trying to do. And if you think about it, all these molecules are just vibrating. And the material people don't really know whether or not the loss of diffusive motion is actually causing more of this kind of vibrational motion. We call it fast motion over short distances.
They really have little hands like that?
Exactly. Exactly. We call them ligands. So what we're going to do is explore that more, but in a structural way. And this is Danny Ballesteros, who worked in my lab, and he developed this kind of approach to studying seeds. So we can do it. What it basically is you put a probe on the material. DMA is really good for looking at solids, so it's one of my favorite instruments for that, but it's really hard to do with a seed because the geometry is so hard, so interpretation is difficult. And you can see that we have like a poor little soybean embryo that's on the bottom of a probe, and what you do is you put the probe on it and you measure the deformation, and then you measure the recovery. And so that way we are actually measuring that compression and then the molecules coming back. That's elasticity, and that tells us an awful lot about the structure. So what Danny has found is that we can look at, this is a hard graph, but you'll understand it in a second. But what I have on the x-axis is temperature. That's a typical temperature range. And on the y-axis is some kind of measure of that mobility. What he has plotted there is your basic scan. And you can see a couple of transitions that we can measure. And those transitions are called relaxation. And it's basically about as the temperature increases, then those pores that I talked about, they also increase. And so there's a relaxation, and this type of motion is allowed. So we can see this for this particular seed tissue. And let me see if I can do it. So you can see right at the higher temperatures, this is in fact in a glass. At the higher temperatures, you really have to warm it up a lot to see the diffusional motion. But you can measure the rotations, and you can measure even those vibrations when the molecules are really close together. And we can quantify all of this now. So it's getting to be a very powerful tool. So point number 2, molecules will move no matter what you do. We can't cool them enough to slow that down. So point number 3, you will always have change. You will always have change. You can slow it down, but you can't stop it. And you know this intuitively. These are some pictures from archive. They call it the Hall of Horrors. But here are some things that happen to paper and other materials. You know, when the rubber band snaps because it's too old, that's a solid aging. And when the paper gets yellow, that's aging. When the paper gets the paper clip marks, I think the photographic film, that's not quite a solid, so it's a little bit different, but you get the point. So we want to study these. We're moving into where we are as of like last week. And what we want to do is understand this in a more physical, chemical way, and we want to be able to manipulate it because we've already told you that the movement is going to happen. So seeds are complicated, so we've really entered into the phase of a single cell because we can manipulate the composition of a single cell. And I didn't tell you with the recalcitrant seeds that we can add chemicals to them and prevent water. So we know that we can form different types of solids just by the composition. So that's why we want to go to a single cell system, just so we can control it better. But what I'm going to show you is some data that we just analyzed about the fern spores because we have it. Danny started these, and he started doing it for his PhD thesis in about 2006, and we've been curating those since then. So just last fall, we pulled them out of the freezer. We do this on a regular basis. and did a viability assessment as well as some other assessments. So that's Lisa Hill. Anyone who works with me has contacted Lisa Hill. She runs my lab, and she is amazing. And Ryan Lynch, who just lost, but he was a student who was working on this project. So here's some data. I can't do this stuff without data. Storage time is on the x-axis. Germination of the fern spores is on the y-axis. And storage time is in days. Just to give you an idea of the time frame that we're working on, 3,650 days right here. That's 10 years. So this is a long temperature. This is a long time scale. And to do anything, remember, it's slow. So to do this, we actually have to have this kind of time frame. But you can see with Pteris vittata, that's a long-lived spore. This amazes me. We stored these guys at 45 degrees. Yep. And they survived for about 3 years at 45 degrees. That is unreal. They're still, they're showing, I have some that are still alive at 35 degrees. But I show you this, we can't even complete the graph because after 10 years at room temperature, they're still pretty good. So this is an example of something that survives for a very, very long time. But we have the other side of the story too. So these are horsetail spores. They're green spores, so there's anecdotal data to say that green spores are slow. Are fast aging, and most of the ones we've tested are. But you can look at the scale. The scale is about 2,500, so less than 10 years for these. And notice that we're looking at minus 176. This is in the vapor phase of liquid nitrogen. And right now, the spores that we harvested in 2010 are completely dead. And it's like, whoa. We thought that if you put something on liquid nitrogen, that would last forever. It doesn't. It's about that mobility that we're talking about. It happens. And so that is rather sobering. Okay, so in one of the typical ways that someone is going to look at the temperature effects is what they call Arrhenius plots. Arrhenius lived in the 1880s and discovered this, and we use it still. It's really very convenient as a way of looking at how temperature affects rate. And what I plotted are a lot of the different species. This is just a cross-section of the species that we've worked with. There's the equisetum. There's the Pteris vittata. And what you can see is, wow, it's pretty linear. And that for all these different species, that line has about the same slope. This is amazing for us. What this means is that if we can understand one point on the graph, we can actually get just about anything for the fern spores. And this is going to change how we do business at NLGRP, because if we can store something, a small subsample at 25 degrees, say, and get an idea of when that is actually aging, we can actually predict what it's going to do at lower temperatures. So it's going to be something that's going to change how we work with. But remember that we have a lot of seeds at NLGRP, so I don't know if that's going to work with a rare species. But this is a very powerful graph for us to know, one, that it is linear, and two, that just about everything has the same slope. But when we extend that temperature range, this is minus 18, and when we extend it to lower temperature ranges, so that's minus 80, that's the minus 80 freezer, and there's the liquid nitrogen vapor, we see, and this is what I just showed you with equisetum, we see a really, really different relationship. And that is, I think, why we're seeing this deterioration in liquid nitrogen. If you look in the pharmaceutical literature is very rich in this, and it makes sense because what they're trying to do is control dosage. For those of you who don't throw away your medications when the expiration date is on, they want to predict what's happening. And they actually came across the same thing, that in the solid state, you can see a lot more deterioration than expected when you go below certain temperatures. And what they're thinking is it's these frustrated motions, it's the escapes that happen with these frustrated motions. So that is the new approach to a lot of the materials, is the degradation. Another thing we see, and this is actually the inspiration for the title, is that we would call it a temperature anomaly. Here's 5 degrees, and this storage right here is minus 18 degrees. And how many times, especially in Hawaii, we see this quite frequently. These materials that you stored them in the refrigerator and you stored them in the freezer in a side-by-side test, and the refrigerator did better. We hear that all the time in the fern spores, actually, and that's why most people who do fern spore banking store them in the refrigerator, not the freezer, because they think the freezer won't store them. Well, that's a lot of anecdotal, but we can repeat that data, and we can repeat it a lot. It doesn't look very significant here, but when you actually don't do it on a log scale, it's really obvious when stuff dies in the refrigerator faster. So we want to understand that. We're going to go back to the workhorse of the lab, which is differential scanning calorimeter. The calorimeter is actually the action word for this particular instrument. It's just about energy, and anything that has a change is going to emit some energy, so we're measuring it. And in this particular case, we're measuring lipids. Everything I've talked to you before about is the aqueous domain, but cells are complicated. They have a lot of different, and oil and water don't mix. So we're going to now look at a material that's more like a composite in the materials where it has different materials that have different phase behaviors. So we're looking at lipids, and this is a typical, you guys might think of it as squiggles on a graph, but I look at, wow, this is amazing. That's a different perspective. I don't get out much. But if we cooled this guy down to minus 150 and warm it, this peak here is the lipid melting. And the experiments we did, I don't know of anyone who's done this before, but we had the opportunity, because we had the spores stored for a while, that we could just cold load these into the DSC, so we didn't load them from the warm after they'd been stored. Ooh, I missed a label here, and I'm sorry, I don't know the time, but I'm going to say it's about 2 weeks. But the important one is this one, which has been 7 years in the freezer. And you can see that, I hope you can see, that there's a lot of differences between this shape and this shape. For one thing, it's moving to the higher temperatures. For the other, it's getting bigger, sharper. And what that means, you know when you put your olive oil, good olive oil, in the refrigerator and it forms a scum and you throw it out because you think it's growing mold? That's not mold. That's the crystallization of the lipid. And it's happening in your refrigerator. And it happens with time because those crystals are moving warmer. So it just means you haven't shaken it up recently. It's not growing mold. So we can look at that at minus 20, but we can also look at this same thing over, these were put into the various storage in 2005, so that's about 12 years later now. And you can see that there's really a lot of difference between storing them in the refrigerator and storing them at liquid nitrogen. Liquid nitrogen actually looks a lot like the original scan. So we can not only measure the mobility in the aqueous phase, but we can also measure that mobility in the lipid phase and combine those two into models that tell us how much motion and make correlations. We're using spores and pollen because it's easier and we know where we want to go in terms of controlling all of that motion and measuring it. But I have the amazing fortune and honor to work with these legacy experiments. And the whole point of these experiments, they were put in the 60s and the 70s, and to just measure this with time. So we can truth all of this with seeds, and it's very repeatable. We're coming out with it now because it was so surprising that I didn't want to publish it before this time. But we're pretty understanding. So I think we're going to come out with a new model for how seeds behaves. The orthodox seeds and the recalcitrant seeds. And more and more, I was just talking with Mike Way, we're seeing these seeds that we call, I hate the name, intermediate. And what are these? These are seeds that you would say don't do well in the freezer. These are seeds that I would say are on this cusp between the fluid and the plasticization, and many things can happen. So we're understanding it. We see these kinds of seeds much more in tropical species, but one of the experiments, we call it the sealed can experiment that Louis Bass started, used soft flower, and back then they used Fahrenheit, so he's got a 90, 70, 50, 30, 10 degrees Fahrenheit as variables. And he's showing, we're measuring really clearly that soft flour, which is high lipid, is aging much faster in the freezer than at 5 degrees. We can repeat this a lot, and we can predict it based on the lipids. So those of you who have heard me, I want to look at, do a DSC scan and find out what the lipids are doing. This is what it's about. We're making predictions, and the predictions are pretty good. You might also want to know how, seed storage, we've been working with recommendations for how to optimize your seed storage for several decades. And I've been part of that. And what is the context? Is this actually changing those recommendations? And I think yes, I really do. Because most of those recommendations are built on viability equations that were models, and most of those models are actually telling us how to get into this glassy state. They're not telling us what happens in the glassy state. And a large part of the controversies over these equations in the past have been the breaks in the model behavior. And those breaks are because it's not a fluid anymore, it's a solid. And so the principles are completely different. So I think what we are going to see is changes. I don't know, are you going to bring some of the changes in the SOPs up? This thing? So we're going to be talking about some of those changes and what consequences are. But I do want to assure you that, we've been doing this a lot, and we're pretty confident that we're on the right track. So that brings some questions about whether or not you should put your materials in liquid nitrogen versus conventional storage. Big question. Everyone says, I want mine in liquid nitrogen, right? Yeah. Well, it's complicated. There's an economic issue in the first place. So if you go to NLGRP and say, I want mine in liquid nitrogen, we're probably going to push back and say, well, that doesn't come free, guys. So there's that. But I also showed you that liquid nitrogen, the temperature benefits of liquid nitrogen aren't exactly what we think yet. And we do know that, I talked about those frustrated molecules. If you frustrate them too much, you'll get faster aging. And I have lots and lots of data where I have better storage at minus 18 than liquid nitrogen. We're still working on that, and that's one of the reasons why we're going with these single cell systems to explore it. So for materials that we know don't store well at minus 18. So those equisetum, they have to go into liquid nitrogen. And we do see a temperature benefit. It's just not what we had hoped for. So liquid nitrogen will always, usually, if you don't abuse these things and over dry them, you will always get a better longevity. There's no question about it. The question is whether it's economically beneficial to you and to us to do it. Okay, so that's, and we can discuss it. This is a discussion point. The other thing that I'd like to talk about is the frequency of monitoring viability. We already know that these things are going to die in storage. We can't stop it even at liquid nitrogen. It's inevitable. So how do you know how fast your seed is? I got to tell you that the materials that you are working with, no one has ever looked at before. So you don't know. I don't know. We're trying to do predictions, and we're working really hard. All of this physical chemistry has led us to much better tools to monitor without consuming your seeds. So right now we're working on an RNA integrity assay. Now, granted, it's with soybeans, but we've tested it with a lot of crops, so I think we're about 20 species into it, and it works beautifully. And the statistical power is phenomenal. It would take 200 soybean seeds in a germination assay, and we can have the same statistical power with 5 soybean seeds. So that's great. If you have a tiny seed, you're going to need more seeds. But 200 to 5, that's great. It means that we're not going to consume seeds up just by testing them, because I don't want that with our valuable collections, and you don't want that with something that's endangered and you use it up by testing. So we're good with that. The DMA work, that's harder because of the geometry. The calorimetry work is working very well. If it has a lipid, we can do really good monitoring, and that's completely non-destructive. So any of you all who have sent seeds to me, that's part of the assay, is we just put them, if they have lipids, we check to see if they have lipids. We run it through. We're not using up the seeds. We're actually keeping that little pan, well, it's like that big, and we're just monitoring it over and over again, and it's a test. So it benefits me because I get a proof of concept, and it benefits you as you get your seeds monitored. Is there anything? Oh, and we're also doing a breathalyzer test on seeds. That's kind of complex, but it's working pretty good. It's kind of like a metabolomics of everything that can go bad in a seed, and you can measure it and trying to sort out what is really bad. So it's not my favorite today, but I mean they have breathalyzer tests for pentane for humans with aging and liver disease, and it's the same principles. So I want to give you just the end of, we're having a seed longevity workshop. The first one was in Germany in 2015. Who would ever think that seed longevity would be so important to people? There were 250 people at that workshop on seed longevity. But we're thinking in the United States it'll be a little bit smaller. The idea with this is to merge a lot of the ecology aspects of seed longevity in the soil seed bank, and how do you work with wilds. I don't think the Europeans are as interested in that as the Americans are, but we'll merge that with some of the molecular biology of deterioration and longevity. So that is in Fort Collins at the end of July, and I would love for you to sign up and come. We'll have some really good discussions about. I'm the host, and I'm going to try to keep it in a workshop format. So we're going to have some good discussions about SOPs and how to fix them, and we're going to have some good discussions about moisture and how moisture affects longevity. So I think it should be a good time. And Fort Collins, by the way, is the microbrewery capital of the world. So, thanks. So I can take some questions. I will.
Okay, so back to your Arrhenius graphs.
Mhm.
I almost hate asking this question, but it's been a long time since I thought about that. Could you just run over what the axes on your graphs are?
Sure. I'm just going to have to go back up because I don't know where I am and how to. Okay. Let's go to the easy one, which is the first one. The question was, explain the Arrhenius plot. So, Arrhenius, 1880s, basically what he was trying to do, it originates, it originates with a Boltzmann distribution, which is essentially how molecules move with temperature. And if you remember some of that, it's always with 1 over T. And in those days, they invented Kelvin. So not only is T temperature, but it's temperature in Kelvin. So that's a really important point. So 1 over 273 would be 0 degrees, is 0.036 or something. So I multiplied by 1,000, just so I didn't have all those decimals. Okay, so you can forgive me on that one. But basically, this is the part of, it's a Boltzmann distribution and looking at it. The other part, this is the age. Well, it works, so I'm not gonna make fun of them because it works. But 1 over T, and you can, in Boltzmann distribution, ideal gas law, all of those, RT equals PV equals nRT. You see that constantly in PChem, and you can interrelate them. So it's actually, the slope is an RT. The ideal gas law is involved in the slope. The other part is the natural log, and it's the natural log of a rate. And I didn't explain this rate, and I should have better, but I was worried about the time of it. But breaking it down, I've expressed rate as a P50, the time for 50% of the seeds to die. There's a good reason for that. I'll draw a graph in the air. If time of storage is on, I actually have a graph. I don't need to show a graph in the air. Hold on. Yeah. Okay. These are all plotted, but what you can see, it's a less beautiful graph than what I could draw in the air. But funny about data. But anyways, you don't see any change, you don't see any change, you don't see any change, and then it starts crashing. And that makes the kinetics so difficult in aging. That's one of the reasons why it's been a challenge for most of my career to find these other assays, is because what are you going to correlate with something that doesn't change? So the correlation is hard, but I digress. This is P50 right here, that hashed line. So that's P50. So I'm using just a math trick, 1 over P50. P50 is time. 1 over P50 is 1 over time. Rate times time equals distance. It all works. So when I look at the natural log of a rate, which is a mathematical conversion.
Okay, so this is like the half-life of your seeds versus a measurement of temperature. Okay.
Is that all you wanted?
That's all.
What? The half-life of seeds versus a measure of temperature. Sometimes less is better. Yes.
A few slides further in, you had a different y-axis that I didn't recognize. Could you?
So into this
Yeah.
other way. Okay.
Forward in the talk.
You guys want?
Towards the end of the talk.
Okay, yeah. You guys want to see my data?
No, I just wanted to understand your y-axis, not that, but the
This one, a DSC scan?
power. Yeah, power.
Yeah. Well, because it's calorimetry. So calorimetry is energy, and energy is usually joules. But the way that the output of the scan is the amount of energy it's putting in, so that's joules per second, which is watts, which is a power. But it's easily converted to energy. Yes. Okay, so the question is, let me see if I can paraphrase it. How much do curators of the seed collections need to be involved in the viability assessment monitoring? Or is there a predictive tool that, as they come in, we'll know? Is that good?
That's good.
And we're not there yet. But I hope to be, at least for agricultural species, and sorry, I do work for USDA, but the other reason why we're working with agricultural species is we can use up an awful lot of seeds and not feel bad about it. So soybeans, my pet. It's well characterized. We understand how it behaves in different circumstances. It's complex because it has oils. I mean, I really like soybean seeds. I like pea seeds. I like lettuce. I like seeds. But we can use these a lot, and they're well characterized. The stuff that you guys are working with, there's no characterization. And sometimes I can't even get the seeds to germinate. So how are we going to correlate the longevity if we can't, or look at longevity with storage time if we can't even germinate the stuff? So what is our solution? And if you guys looked at the time scale that we're looking at, I mean, I may be overconfident, but I think that every single seed bank should be able to get at least 50 to 100 years out of their seeds, unless they're on that brink that that they're intrinsically bad. What?
Intermediate.
Yes. So, just 1 minute. So, what we're trying to do, because we don't have the seed analysts to do a monitor, we don't have the seeds to monitor every 10 years. That's what the standard is right now. That's crazy. NLGRP, well, we're just celebrating a budget increase. Yes. But, and that means that we will be able to put more seed analysts on. But at current budget, we're on a monitoring frequency, and this is scary for us, of about 60 years. It's unsustainable. And if you think that you have to use at least 50 to 200 seeds of these very valuable, well-curated seeds to do it, that's unsustainable. We can't do it that way. In my opinion, and Joyce and I have worked a lot on this, we need better standards or something, advice maybe, guidances, so that we're not using up our seeds just by testing them. I think right now I love this RIN assay. It's automated. We can go deeper. The data is really, really deep. It's beautiful. It's robust. It's highly repeatable. So this is something that we're going to invest in, and we're beta testing it next year. And incorporating it, we're hoping that 5% of our collection will be RIN tested. And that also gives the seed analyst a new technique and will help them grow professionally. So that's one. Another way we're going to do it is, but we'll do it in a smaller percentage, storage at high temperatures, knowing the temperature relationships. And then not even touch the seeds in the freezer. I don't want them coming out. We think the temperature fluctuation causes damage, so they are going to stay in there. So yeah, I think there's a lot of things that we can do to improve our methods, but ultimately, the seed experts have to be the curators have to be involved in their collections, and we wouldn't want it any other way. They have to. This is a highly professional, and I think technically demanding, I would say experiment. I mean, we don't know where we know where we have to go. Getting there is the challenge. Peter.
Well, if you're in Texas, I just want to...
I am in Texas.
Oh. We're all in this vote. I knew there was some problem. If you're trying to...
So you're asking me...
non-GMO
So the question is, looking at the botany of the United States,
Yeah.
what proportion would I put in cryo, and what proportion would I put
Well, that's one thing I'm asking. Yeah, what's that?
conventional? I don't know. I'm not a botanist. I mean,
Leave out Hawaii.
yeah. No, we do not want to leave out Hawaii.
What are some of the groups, well, name, I think for the audience, some of the groups that are going to need cryopreservation in the United States.
I would say I can't even possibly estimate the proportions. What we're trying to do, I mean, because I just don't. I mean, I know what I've looked at, but that's not the way I would approach the question. I mean, the way I would approach the question is, let's get some good analytical tools that we would know, and some of those analytical tools might be surprising. For example, in wheat's a common example. We can get what we estimate is about 400, maybe 500 years in the freezer. It costs about $10 an accession to regenerate it, and it's a self-pollinating species. Why would we ever put wheat in a cryogenic storage when the freezer space, I mean, have you seen our freezer space? I mean, just putting a bag in, it's costing us nothing in energy. And a liquid nitrogen platform costs us a lot. So we're going to approach this very much on a cost-benefit basis. I mean, we have to. So if we're working on a tree species, trees are really hard to regenerate. They need a lot of real estate, and they take a long time. So that's going to be some curator's time over a 30-year part. So, and I got to say, I think trees make wimpy seeds for a lot of wimpies. I mean, they don't last long.
Oh,
Wimpy. So I would tend to put tree seeds, store them cryogenically. The wimpy seeds. But I got to tell you, I mean, this fraxinus problem, we're just getting hundreds of accessions of bags of seeds. And it's like, what am I going to do with that? I can't put that in liquid nitrogen. We can't afford it. So, I mean, there has to be some conversation about prioritization that we will do cost benefit with this. I mean, so I didn't go with the physiology. I went with the cost.
In principle, would you, if you had 5...
I am never going to answer the question that you want me to. No, I'm going to answer that one. So he's asking me, am I going to make a prioritization based on rarity?
Well, yeah.
Okay. No, I work for USDA. That's not in our mission.
I'm asking you to advise these institutions
And
that have made a prioritization on rarity.
my
How
advice...
effective they can expect their activities.
Yeah. My advice is you have an exit plan. I mean, if we can get you 10 years and that's buying time, good. Freezer's good. If you have no idea, you're just collecting these seeds just to collect them, why are you wasting my time putting stuff on ice that you have no idea what you're going to do with? They're going to die anyways. I mean, this is an ethical issue for me of making a collection that you don't have the utility built in. We got to have the utility built in. I know, I got a lot of people upset. I work for USDA, you guys.
No, what utility built in?
The utility for you is a conservation mandate. So I really would like to see that you have that expiration date in your head before you put them into the seed bank. That's my own philosophy.
A short expiration date.
Not a short expiration date. If you say in 100 years from now we think we'll have habitat, you get liquid nitrogen. Chris.
Well, actually, that's a general thought.
So the question was, how do we make a plan for extraction? One of the reasons why I wanted Chris to come and talk to us today is because what she's presenting to us today is a paradigm shift for us, right? What we thought we could do was collect those seeds, send them to Chris, and they were fine. And we could check off the box and we could go, yeah, got that species done. I can go out and get this other one. And what she's presenting to you today is it's not quite that simple, right? There are some species that are very long-lived, that have great dormancy. They'll do fine in the freezer for years, but there are others that are very short-lived. And so our conservation program must include this aspect of what's going on with the sustainable populations in the wild. This ex situ bit that we've been doing is absolutely integral to that, sustaining the wild populations, right? It's exactly the title of Ed's book. You know, what we do in ex situ is part of what we are doing to sustain the wild populations. So Chris and I began the protocols with this mission in our heads, and we're communicating that to you today, that you can't just collect those seeds, send them to Chris, and think that you're all done. You can't just go, yep, got that one, moving on. What she's trying to express is that you have to have this exit plan in your mind. Okay, maybe it is that you need to take the seeds back out and regenerate them and then put them back into storage again. You have to bulk them, put them back in if there's no place for them to go in the wild. But all of this is stuff that we'll be talking about more later. But seriously, I know that it's a paradigm shift. And I know that it's a little shocking to realize that. It was shocking to me. And some of the percentages that I've heard in answer to Peter's question of how many of these species can we expect to be orthodox and long-lived in storage versus short-lived is, up to 70% of the species we're working with could be in that short-lived arena. So I'm.
Do you repudiate the article you read in Science?
Well, first of all, it was an opinion piece. So you can always no, everything of that is absolutely correct. And remember, that was for recalcitrant seeds, and it was saying that we can.
What the proportion would be.
Yes, and I don't think that that's particularly changed, and I think that. In North America, I mean, everyone worries so much about recalcitrant. That does not keep me awake at night. What keeps me awake at night is actually things like the equisetum spores, where I did everything right, and I got 10 years in liquid nitrogen. And yeah, fast aging is fast aging at all temperatures.
Manifestly different, though, or do you get seeds that do that too?
The temperature dependency is exactly the same slope for seeds. I just didn't show you that data.
The thing that I don't like while they're there.
Well, I don't think anyone, I certainly hope I wasn't interpreted as saying don't do this. But I am going to quote a famous person, Ollie Ryder, who's one of his papers was very, it was an opinion piece too, and it was very defining for me. And he said, nobody is going to thank me for putting away some DNA. And I've taken that to...
Seeds, right?
Well, I mean, I could say the same thing. No one is going to thank me for putting seeds on ice. Well, but I do think that, I mean, we understand scientific collections. And when I look at it from that perspective, not from a conservation perspective, then it's about taking care of and curating your scientific collection. And I have absolutely no problem with that. I also think that as human beings, and this ex situ amazing experiment that we're doing, is humans contributing to using their science to do something that's fabulous for the earth. And I mean, I just presented, who would have ever thought PChem would be involved in seed storage? And it's like, I mean, the engineering, the science, this is not an insurmountable problem, but it is a problem if we don't put it on the table and say, we got to do better, and we got to look at it. If we know how to grow these things, hopefully we do, we're buying time, you regenerate them. get a fresh batch, and put them back. But just allowing seeds to die because you didn't know, you did all that problem to collect them, it kills me.
It's a huge resource.
I don't remember anybody saying that that's what you should do, though. I just don't.
I would like to see an exit plan. And I'm arguing in my agency, to not only have it, well, we have an exit plan. We don't collect anything without, but would you put a timeline on for us? Because we don't want to have the responsibility of indefinitely until I want them. I mean, if we're scientists and we're doing this, then leaving it up for almost a faith-based whenever that's not where we should be going. I mean, and I'll just leave it at that. Okay.